and he's going to talk about Quantum Yang Baxter Equations, Nambu-Goldstone theorem, and black hole information. Take it away.
Okay, so it's a pleasure to be here. My name is Ivan Arraut. From San Joseph in Macau, where physics is more or less starting. My PhD is from the University of Osaka. They changed the name now, no? It's not Osaka University. It's the University of Osaka. My supervisor by the time was Hosotani Yutaka. But I did the last year in KK, High Energy Accelerator, where I collaborated with Hideo Kodama, my last year of research. Then this is more or less my academic history after some JSPS position and some postdoc position until I reached Macau. Everything has been in Asia. Today I talk about Nambu-Goldstone theorem, Quantum Yang Baxter equations, how the Nambu-Goldstone theorem emerges from these relations, and a little bit about black hole information, because there is a way to formulate the Hawking radiation as a mechanism of spontaneous symmetry breaking, if we find the right Lagrangian, etc. So the content, let me see, is not changing. Okay, now it's changing. So the content, first, when I was explaining internal, external symmetry, internal, well, external, when we talk about space-time symmetries, basically. I will explain, of course, for completeness, why it's a spontaneous symmetry breaking, and then the Nambu-Goldstone theorem. Then discrepancies between, actually, this should be, in reality, it's not relativistic, it's Lorentz violating versus non-Lorentz violating. And I think actually I put the wrong. Let me check something. 1 second. Yeah. 1 second. Because I think this is the wrong presentation actually. The right one is this one. Yeah, it's this one. So which share is this one? Sorry. Yeah, no, the Zoom meeting is just for this one. 5. Okay, now it's true. So yeah, discrepancies between Lorentz invariant and Lorentz violating situations, because there are some Hamiltonians or Lagrangians where the Lorentz symmetry is explicitly violated. It doesn't mean that there are violations of unitarity or so, because as far as the PT symmetry invariance is accomplished, they satisfy unitarity. In the case of non-Hermitian Hamiltonians, for example. And I will explain the generic character in Nambu-Goldstone theory and the connection with Quantum Yang Baxter equations. Spontaneous symmetry breaking and black hole thermodynamics, Hawking radiation as a mechanism of spontaneous symmetry breaking. Now, of course, as I mentioned, this is not a big deal. Of course, for any symmetry, when you have the action, this action has to be invariant under the set of symmetries which the system has, invariant to total derivative. Now, this is just an example of internal symmetry, the permutation group, which is and now let's go directly to what is a spontaneous symmetry breaking. We have a Lagrangian. This is the quadratic term, the typical potential, where spontaneous symmetry breaking appear with 2 free parameters, mu square and lambda. And let's say we have this transformation, and this Lagrangian is invariant under this transformation. Of course, the potential also is. If we find the minimal or the string conditions for this potential, we find two results, one trivial and one non-trivial. The trivial is when mu squared is larger than 0, and the non-trivial is when mu squared is more than 0. And this is equivalent to changing the free parameters of a system. It's like changing the temperature in a ferromagnetism, for example, such that the symmetry gets spontaneously broken in some limit. And of course, collective behavior emerges. It's like when we have this ferromagnet with all the magnets pointing arbitrarily in different directions. Then the total magnetization is 0. But if we decrease the temperature enough until at critical temperature, then all the magnets will start to point in one direction as long as there is external perturbation, very small enough. So it means a minor perturbation helps the system to select one ground state. Then let's assume, of course, the system was comfortable in the center, which is equivalent to be here, with zero magnetization. Then the center becomes unstable. It's in equilibrium or unstable. And any perturbation, any should or any make the system to select one ground state. And it comes out that the direction or the vacuum selected depends on the direction of the perturbation. So for example, here, if the magnetic field is pointing in a different direction, then all the magnets will point. It's equivalent to selecting another ground state. So when it happens, the vacuum violates the certain symmetries. We call them broken symmetries. Spontaneously broken is because the Lagrangians still satisfy them, or the Hamiltonian. And the effect of that generator, or those broken generators, is to map the vacuum to another one. So it's like when you're in this Mexican hat, if one vacuum is selected and you apply the broken symmetry over this vacuum, the vacuum will be mapped to another one at the bottom, another degenerate vacuum. So of course, there are many ways to demonstrate this theory, etc. But let's go step by step. This is an arbitrary selection. Of course, the ground state will be selected with one non-zero component here. This is a standard decomposition. It's a way to see how many gapless particles emerges on Nambu-Goldstone fields, which in this case is represented by this by K. So if we want to see more explicitly in Nambu-Goldstone theory, we have to expand the potential up to second order. The first order term disappear because it's around the equilibrium condition, and the derivative of the potential at the equilibrium is 0, as the condition here suggests. And this is the mass matrix with the mass elements square larger than 0. And it turns out that when the symmetries are broken, the terms here become 0. So that guarantees that the Nambu-Goldstone bosons are gapless. No? There are other ways to demonstrate the gapless condition for Nambu-Goldstone fields. And in general, when we have a Lagrangian with kinetic terms and potential terms, we have a group, a series of generators of that group. They break the symmetry of the ground state, but there is a subgroup of that group which still doesn't such that the ground state still satisfies the symmetry. So, and this subgroup is important. And then the Cosell space, which is defined mathematically, the dimension of that coset, which I didn't write here. Well, the Cosell space, the dimension, defining number of Nambu-Goldstone bosons. Nambu-Goldstone bosons. Well, these are just formalities. You have a unitary operator, you span, and this is a way to see how it operates over the ground state. And then the idea is when you see the second order terms in the potential in the expansion you saw before, when you operate over the ground state, when that operation is trivial, when it doesn't change the ground state, of course, this term could be non-trivial. On the other hand, when the generator violates, is a symmetry violating by the ground state, then of course this term becomes trivial, and that guarantees the Kaplan's condition. In other words, when this is zero, it means the ground state satisfies the symmetry, and then of course this is trivial. But if this is a broken symmetry, of course this is non-zero. These two guys are non-zero, and necessarily the mass terms are zero. So that guarantees the Kaplan's condition. Now, a more formal way to analyze the Nambu-Goldstone theorem is going to the conserved currents. We have the conserved currents, and we can define the charge as the integral in volume of the zero component of this current, which will come out to be the broken charge in the long term. I will tell Lie algebra structure. This is the definition of the unitary operator. The standard definition of vacuum is guaranteed when the charge or the generator of the group annihilates your state. However, when you have a degenerate vacuum, the broken charge doesn't annihilate your state. And that means that when you operate with more properly, so when you operate with U over the ground state, this vacuum is mapped to a different one, to a zero prime, different ground state. This is my definition of order parameter. Is the commutator of the broken charge times the Nambu-Goldstone felts, which in the standard decomposition, sometimes they put phi 2 to this and phi 1 to this. I will show you later. And this is another representation of the order parameter condition. The vacuum expectation value is different from zero when the symmetry is spontaneously broken. This expression will be important because later when I introduce a double commutator, I introduce this algebra condition here, I can extract the quantum Yang Baxter equations from that expression. And why to extract the quantum Yang Baxter equations? Because they help you to explain naturally the problem of counting Nambu-Goldstone bosons in condensed matter systems, and also the dispersion relation, which comes out to be quadratic in the case of Lorentz violating systems, not linear as is the standard case. No, and the Nambu-Goldstone theorem has an apparent violation in the case of condensed matter systems. Normally, number of broken symmetries is equal to number of Nambu-Goldstone bosons, but in Lorentz invariant system, two broken symmetries could give you only one Nambu-Goldstone boson with quadratic dispersion relation. And some people call these symmetries redundant symmetries somehow. So we will analyze, I will show how to analyze the part subsequently. This is a convenient decomposition, which I was mentioned before. This is another parameter. When I put SB is single vacuum state, for distinguishing from the fact that later I will sum over all the vacuums. Because the idea is that when you sum all the vacuums, for example, if I put summatory of 0 here, all the vacuums, over all the possible order parameters, that's equal to 0. I recover the original ground state because it's like summing. This is like going to this Mexican hat and summing all the vacuums. There is always one negative number for each positive number. Then you can recover it. So the superposition of all the ground states gives you 0. Okay, we are now here. Great. Now, this is the same decomposition, the same commutator I showed before for the charge. This is the charge density, and this is the Nambu-Goldstone factor. In this case, will be phi 2 actually. You could put perfectly phi 2 here, and it's just the same. Here, this is a summatory, this is an identity. This is identity because it's a complete set of intermediate states. And you sum over all the complete bases and you get identity. So it's like introducing something which doesn't change the result, and still ground state. Equal time commutation relations different from 0. Now, this term depends on y, space-time index. Then you assume space-time translational invariance. The space-time translational invariance means that I can write this current is 0 is like like this. correct? Yeah. So, and of course, you have to take into account that this is Lorentzian metric, so it will be energy, zero component, minus momentum, the exponents, no? Then that's why you see that these exponentials appear here. Because you have to operate those exponentials over the kets, the Bragg kets. Applying over this n gives you this one, and operating over this guy gives you 1. Exponential to 0 is 1. Now, here what happens is that we execute the integration over the volume of the exponential, the spatial component of this exponential, and this gives you a delta Dirac. This delta Dirac in the volume is telling you that the momentum has to go to 0. That's why it's telling you. This is non-trivial when this goes to 0. The demonstration finishes when you can demonstrate that this Mn has to be 0. And the only way to demonstrate that this Mn is 0 is by demonstrating that this expression is time independent. And that time independence is demonstrated if you prove that the derivative in time of the original expression is 0. And that can be demonstrated, of course. It's a demonstration that is done in some textbooks. You can demonstrate that this becomes in this form. The integral in the volume is the divergence in the surface. And then, of course, if the volume is high enough, then this becomes 0. That's the demonstrate that then that this is this turns here as 0. So it means that the particles, the intermediate particles, the Goldstone bosons are Nambu-Goldstone bosons are gapless. They go to the momentum and the energy goes simultaneously to 0. That's a way. That's very important. But in this case, in both cases, go linearly to 0 simultaneously. Then now, dispersion relation is important because it was found, it was investigated. Nissen and Chada, many years ago, investigated the problem about why the Nambu-Goldstone bosons in condensed matter systems, they have quadratic dispersion relation and nonlinear, and why 2 broken symmetries seems to generate only 1 Nambu-Goldstone boson and not 2 in some cases. And that's another problem. And then even Yoichiro Nambu mentioned that in one paper, I forgot which reference, but for sure he knew, because he was one of the guys who translated these ideas from condensed matter to high energy physics, which gave him the Nobel Prize. Watanabe, Murayama, and Thomas Brauner, they investigated that problem. I forgot which year, 2013, 2012, 2015, those years, between 2010s, those years, they were working in this problem. Thomas Brauner, who is now in Europe, somewhere, I forgot where, maybe Denmark also. Watanabe should be in the University of Tokyo right now. And Murayama, who is in the Berkeley, no? University of California, Berkeley now. He was the former director of, he's the former director of the IPM, the first director of the IPM. Then, of course, they explored this problem. They developed some rules, and their approach is correct, but I decided to do a different analysis. And by doing this different analysis, I realized that the Quantum Yang Baxter equations emerge naturally from the order parameter condition. So that means that this condition here, this condition, let's call it this order parameter, will give you 4 triangles. And in prime, this is the complete set of intermediate states. This is the degenerate vacuum. The slopes have to be the same, no? You have to keep the slopes. And after, when you exchange n by n prime, you have n prime here and prime and 0. This 0 is, of course, this is like analyzing the interaction of pairs of Nambu-Goldstones. But the third line is a 0 energy, a 0 momentum line, which is equivalent to summing all the vacuums. It's like doing this. assuming all the vacuums, but then this becomes zero. Because this is where you record your inner ground state. So when you do that, you have 4 triangles. And under the exchange of these 2 guys, what you're analyzing is what happens if I exchange the pair of Nambu-Goldstone bosons. But when you do this exchange, you have to change the sign of momentum. Because it's like you have a particle, it's approaching to each other. When you exchange 1, 2, you exchange now 1 here and 2 here. And if you want to keep here, of course, you have to change the sign of the momentum. And that has to be taken into account. When we take into account all of this, of course, some interesting expressions emerge. Well, for the quantum Yang Baxter to appear, I have to promote the order parameter tensor with 2 indexes, not 2 components, 2 indexes, A, B. This is the way to represent this as an R matrix. For me, this will be an R matrix, and it will appear inside the quantum Yang Baxter equations. This can be decomposed if you want to introduce a basis. And still, of course, the broken charges will be also tensors. This generalization is important because otherwise there is no consistency between the indices of quantum Yang Baxter and this formulation. But there is no loss of generality. There is no, actually it's even more general because it can include other cases. And a vector is a special case of a tensor, and a scalar is a special case of vector. So anyway, it's okay to do that. Then I repeat the same as before. This is commutator, Nambu-Goldstone field, commutator, broken charge. But now, assuming Lie algebra, the Lie algebra I mentioned before, I put a commutator here. It's a way to introduce pairs of Nambu-Goldstone bosons here. Complete set of intermediate states here, complete set of intermediate states. It's like introducing pairs of Nambu-Goldstone bosons N and N prime in this expression. Remember that if you assume Lie algebra, the commutator of these guys gives you just another broken charge. That's it. And of course, you assume space-time translational invariance. This is what I showed before here. But now, of course, apply only to the charge. I am not showing the integration. There's an integral symbol here over the volume, which I don't show. But in principle, you have to integrate over the volume of this y and so on. But I omitted it just for feeling comfortable because I don't want to integrate initially. And the reason why I don't want to integrate is because I want to see how the momentum approaches to 0. If it approaches to 0 linearly or quadratically. And the same for the energy. But the energy doesn't appear in the integral, let's say, because there is no time integration here. Then here, of course, there is a sum over n and prime, these 2 guys here. And this is a simplified notation. Instead of putting BA, it's the same. Only that I put BBL for simplifying, but it's exactly the same. So you expand this double commutator, there are 4 terms, 1, 2, 3, 4. And they correspond to these 4 triangles, 1, 2, 3, 4. It can be demonstrated that that's the case. And each one of these terms, this is an R matrix, it's another R matrix, and this is another R matrix. And of course, since there is equivalence between pairs of triangles, this some of these terms can be factorized. It can be factorized. Then this is an example of how to define the R matrices. For example, for this case, 0, M, M prime L, and so on for the others. Then we have these products. These products of, this is Yang Baxter, 1, 2, 1, 2. This is another way to represent the lines instead of putting explicitly the components. Sometimes you can just put the number of the corresponding line. But like this, of course, you have to, it's more comfortable for me to write this way. And in addition, you have to take into account that in the same line, for example, 0 and n has to be in the same line. For example, 0, if there's an n, it should be here or here, for example, that index. N prime L, N prime L should be here or here, and so on with the others, no? And there's a way to construct consistent triangles like that. And this is the component way of the quantum Yang Baxter equation in components. Then, if I zoom over all the ground states, this is another way to represent the quantum Yang Baxter equations. If I zoom over all the vacuums, these three terms, the product of these three terms is equivalent to the product of these three terms. And in simplified notation for not writing everything, LP, B, B, LP, that is. Right? And the graphics are here. This is what I just wrote here. This triangle, Yang Baxter, remember the slopes are represent the you have to keep the slope constant. Yeah.
Why constant two-dimensional system or any dimension?
That's a good question, but of course, if I am assuming the motion of Nambu-Goldstone bosons in the Mexican hat, I am figuring out to be two-dimensional initially, because of course it's just a plane motion.
Well, I mean space-time. So the target space is one dimension, right? But space-time, two-dimensional or high dimension?
So you mean if it's only one dimension space and one in time?
Yeah, so is this what you are saying?
Well, in this simplified way, yes, but I think this could be general, I think. No, the space-time still for me is 4D. I'm just taking it to be Minkowski.
Mm-hmm.
And the ion concern is only with internal symmetries.
Yeah. So
Yeah.
This box just for internal.
Yeah, just for internal symmetries, yeah. The space-time for me is 4-dimensional, and I am taking a space-time translational invariance, which is what I do here. Well, of course, I mentioned something about Lorentz violating explicitly and not explicitly, right? Then that thing I will not use. I will not use the argument. Instead of that, what I will use is a different approach. What I will assume is what happens when n and n prime are different, represent different degrees of freedom, and what happens when n and n prime represent the same degree of freedom. Then that's another way to say what happens when two broken symmetries are redundant, or what happens when they are different, completely different. So because the approach of Murayama and Watanabe was the other way around. They started from the symmetries. Well, in my case, I start from the interaction of Nambu-Goldstone bosons. Then it's a different way to see the same problem, but interesting issues come out. Of course, and this is the first time, my approach is the first one which proposed that the quantum Yang Baxter equations emerge like that. Taking, of course, the explanations from these guys, Witten and Costello. Actually, I attended this conference 2016, and Witten was explaining these quantum Yang Baxters and interaction between particles. Of course, he was explaining that what everyone knows in these approaches that there cannot be particle creation. So, but since this is infrared limit, I think it's okay. And he was mentioning this guy many times, Costello, I remember. So by the time I was already studying the quantum Yang Baxter equations and studying this problem, then I think maybe it's possible to apply these expressions to the Nambu-Goldstone theorem. So you can see that these lines are almost parallel because the momentum of this guy is almost zero, and the energy also. And zero represents a fictitious particle with zero energy and zero momentum. It's just the degenerate vacuum. It's the ground state. It's for closing the triangle. And that's equivalent to sum over all the ground states. That's why I put this superposition of ground state here. And in notation, it appears here. Zero contracted with zero force you to sum all the indices, all the vacuums. And when you sum all the vacuums, you recover the trivial ground state, the original one. And that's why the summatory of zero appears here. So this is another way to represent the quantum Yang Baxter equations. And well, I also have to say thanks to Michio Jimpo, who I had discussions with him. I have to give credit to him. He was in Rikyo University by the time. I was just PS fellow in Tokyo University of Science, and then I visited him several times, and we discussed these issues, and I learned quite well this from his board, actually. Then And these are the first triangles as I did. I mean, of course, I don't like because they don't show the fact that the slope has to be proportional to the momentum, but it's explained more or less what is the relation. These triangles are just the same, and the exchange of particles, n by n prime. Of course, these triangles, the upper triangles and the lower, are not necessarily equivalent. They are just equivalent when n is equal to n prime. If n is different to n prime, they are not equivalent. Then what happens when n is equal to n prime? When n is equal to n prime, I can factorize all the terms in the expansion. These four triangles become equivalent. So it means that in this commutator, which I will go back, it means that these four terms will be the same, but I have to factorize the faces. And I have to sum the faces. And when I sum the faces, at the end, it comes out, the momentum factorizes like cosine. And of course, the energy still keep exponential. So at the lowest order, the cosine expands quadratically in momentum. So that explains that the momentum goes to zero quadratically.
So the
And-
momentum appears here. So this means your space-time is higher dimensional.
No, it still is the four-dimensional space.
Yeah. So what? So in what sense you draw the Yang Baxter equation? Yang Baxter equation has momentum, right?
Yes, it's the slope.
Yeah, but
Yes,
this one is just for 2 dimensions.
Well, you could say that. But generalizing from 2D to 4D is just
example 4-dimensional Yang Baxter equation.
no, I have not done that.
No, I don't
No.
think such thing exists.
No, it doesn't exist. No, this is a two-dimensional representation. But for example, when you analyze several problems in physics, you can use the 2D approximation, and because anyway, what you do when you analyze in 3D, for example, because it's a space and time, no? A space, you can take one-dimensional, and time. In some cases, it matters, but in this case, I think it's not that important because at the end, you can just align your coordinate system such that the momentum is, I mean, the system becomes one-dimensional in a space. So it's just a representation, let's say. No, it's not a. But yeah, your question, I understand why you ask, because in different dimensions, the interactions behave differently. So of course, but here there is no gravity. For example, I am not getting involved with gravity yet. So in gravity, it's quite relevant to have to consider the dimensionality, because gravity behaves different in different dimensions. In other interactions also probably. But here, of course, there is some. We have the Mexican hat, for example, the Mexican hat right here. The Nambu-Goldstone bosons are moving here. This, if you look from the top, this is a 2D surface. I mean, it's just 2D. Then at the end, of course, there's only one dimension in space, which is the circle, and so it's not a. But yeah, I will think about your question deeply, because there must be something hidden in this expression. Now, okay. So what I was saying is that when you factorize all the terms, the momentum goes to zero, but this expansion at the lowest order is quadratic. So it's telling you that when n is equal to n prime, it means that when these two guys represent the same degree of freedom, then the momentum goes to zero quadratically, but still the energy goes to zero linearly. So this is a quadratic dispersion relation. In addition, the problem of clumping is solved automatically, because we are saying that 2 degrees of freedom that come from different broken symmetries became a single degree of freedom. It's like if the Nambu-Goldstone theorem was always satisfied, it's always satisfied. 2 broken symmetries represent 2 Nambu-Goldstone bosons, but somehow these 2 degrees of freedom, they fuse in a single one with quadratic dispersion relation. That's more or less, that's the interpretation I give to these results. So from my perspective, the Nambu-Goldstone theory is not violated. It's simply that the two Nambu-Goldstone bosons merge into a single degree of freedom with quadratic dispersion relation. Of course, this is a way to simplify it further. If you factorize all the terms, this is more evident that the energy goes to zero linearly and the momentum quadratical. And of course, if n is different to n prime, you can never factorize all the terms. And when you group the phases, there is no way to group the momentum such that they go to zero quadratical. That will never happen. So this is a way to represent the motion of Nambu-Goldstone bosons in Mexican hat. And of course, when I zoom over all the ground states, this is what I was talking about. This is equivalent to the emergence of these four triangles, and these four triangles appear. They are only valid when you zoom over all the vacuums. So zooming over all the vacuums gives you the trivial result, because as I mentioned, for every value, for every ground state, there is always one diametrically opposite with negative sign, which cancel the result. That's why you see 1 minus 1, 2 minus 2, blah, 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 until you get 0. And this is the decomposition I said before. And these two expressions are equivalent. This is another way to represent. This is the order parameter in the standard decomposition. This is the Nambu-Goldstone field. The commutator broken charge Nambu-Goldstone field gives you order parameter. Superposition of this goes to 0, and this is what I have applied for explaining the origin of the quantum Yang Baxter here. These are other issues. I mean, this is just additional. This doesn't add up so much, but this is demonstration. Standard demonstration is just demonstrating that the different ground states are orthogonal in the thermodynamic limit. Let's say you calculate the product of one ground state and another one, different one, in the thermodynamic limit is 0. They represent different Hilbert spaces. They are orthogonal to each other. I will mention something else, which is a parenthesis. Now, conclusion is that the Nambu-Goldstone theorem is a natural consequence of the interaction between pairs of Nambu-Goldstone bosons, and this interaction can be analyzed via Quantum Yang Baxter equations. This part is concluded. Now, I want to make a parenthesis. You just mentioned it, that by chance I analyzed the neutrino mass problem by using approximate triangular relations and by taking as an order parameter the neutrino flavor. So I assume over all the flavors of neutrino equals 0 using this mixed matrix. This is the mixing matrix, no? C12 is cosine of theta 12, C13 cosine theta 13, blah, blah, blah. And then I put the picture of the neutrino oscillation, like the neutrino were shifting between three vacuums, muonic, tauonic, and electronic. No, like if the particle in one moment feels that it's in an electronic vacuum, in a subsequent like muonic vacuum, and the other tauonic. And then by doing that and taking this condition, which is what I mentioned before, assuming all the ground states 0, I could obtain from the mixed matrix values for the mixing angles, constraint for the mixing angles, which are inside the range of observations. Of course, maybe it's just a coincidence, maybe not, but still it's inside the range of observations. For example, there is an angle which is 45 plus minus 7, and I obtain like 39 or almost 40 in that angle, and so on. And of course, the problem is that when I use the triangle relations, of course, I put 2 theta to each angle. This is the angle which is almost 45. I use this approximate triangle relation, which are not accurate, because of course the sum of these angles is not 180, it's a little bit larger, but still I wanted to see what happened. And taking the vertex, each line as the inverse of the mass of the neutrino, I found that the order of the mass should be normal. So it means mass 3 is much larger than mass 1 and 2. Mass 1 is approximately mass 2. You know the eigenvalues of masses for the neutrinos, 1, 2, 3. But two masses are very close to each other. The 1 and 2 are very close. The 3 is much larger than the others. This is what I obtained. And the angles are more or less inside the range of observation. Of course, it's too premature to say because I did many simplifications. First, this approximation of triangle. The second is that I don't consider CP violation, which is there are potential CP violation in these processes. And I was remarked at Fermilab in Chicago and the Kamioka, the experiment in Kamioka, they obtained different results for the same experiment. The experiment in Kamioka obtained maximum CP violation, but the experiment in Fermilab obtained no CP violation. So there is a discrepancy between the two observations and two laboratories which are quite serious. So probably the way how they are observing this, the same process is different. So I just wanted to make a parenthesis in this part. Now I will jump.
Do you have standard? So this is totally different from standard model.
No, the standard model will be going to the
standard model must come in car.
well, in the standard model, you will have to. What happens is that the Higgs mechanism doesn't give mass to the neutrinos because, for example, when Weinberg, Salang, and Glashow they did the electroweak theory, the Nobel Prize actually, which is a gauge theory. The Higgs mechanism they give mass to the electron, to the boson C and W, and so on. But they assumed that the neutrino was massless, so they never touched the neutrino.
This is the present standard.
No, the present in the standard model there is no universal agreement about.
So I'm asking. So what mechanism is this?
No, there is no mechanism of mass yet. I have not shown the mechanism. I mean, at this point, there is no mechanism of mass. In this case, I am just trying to explain in a consistent way some constraints emerging from some relations for getting the mixing angles, the parameters for oscillation of the neutrinos, but there is no mechanism yet. And actually, I don't have in mind yet the mechanism because.
No, but we have
assumptions. What assumptions do you make to get those?
Triangle relations and the fact that the flavor, the neutrino flavor is. What do you say this thing? The neutrino flavor is other parameter. Let's say it's like this. For the mechanism that's in process, I am thinking about that. There are many options, but of course, well, I am assuming that there is no steric neutrino, of course, because if you have a steric neutrino, you have the mechanism already, no? So without steric neutrino, what will be the mechanism? No idea. But the idea is that I take one vacuum, there's another vacuum, there's another vacuum.
what
Therefore,
is that vacuum? So what is that vacuum?
For me, the neutrino.
Okay, concerning one electron state, you have vacuum.
Yeah, well, exactly. That's the point. The point is that for me, the neutrino, when the neutrino moves from one point to the other, the neutrino is changing, no, from electronic to muonic down. So you emit one electron neutrino. Remember the solar mass neutrino problem, which
okay, that is okay. We have one vacuum, and on this vacuum we have one particle state.
Yeah, that's the universal concept.
Neutron state is oscillating to new.
Exactly, that's one point of view. But let's say the point of view I am proposing is that the neutrino perhaps feels that the vacuum is changing. From the perspective of the neutrino, in some moments he feels the vacuum such that his electronic in another vacuum. And then, of course, I am taking 0. Morning. These conditions. And this condition constrain the mixing matrices here. These mixing matrix conditions here. It generates some constraint between the mixing angles, and then you can find some more or less consistent results. Now, it doesn't mean, but there's no mechanism here right now.
You should consider some field theoretical model
Well, that's why it's,
Explain this. Otherwise, it's not understandable.
yeah, I agree with you, because that's the next step. Because initially, of course, there is no universal agreement what is the mechanism for giving mass to the neutrinos. So I was trying to do a mechanism which doesn't involve the traditional stereo neutrino or the standard couplings, etc. But I have not done the mechanism yet. What I find is a series of constraints between variables by using some triangular relations.
I'm very confused because how do you generate a mass term without violating any symmetry, without right-handed?
That's a good question that we don't know. But let's say the issue is that here there is no mechanism yet. I have not mentioned any mechanism yet because I have not shown any Lagrangian. I have not shown any symmetry, nothing. And actually, the symmetry, if it exists, let's say from this perspective, what is happening is the following: the neutrino is oscillating between three vacuums from his perspective, but the neutrino never selects any vacuum because it doesn't break the symmetry of whatever the symmetry is, which is related to the flavor. The neutrino is not breaking it. If it breaks, of course, clearly we select one flavor, electronic or mono or tau. But since probably because their cross section is quite small, whatever the reason is, the neutrino probably doesn't interact so strongly, such that the perturbations from outside don't force them to select one ground state. That's more or less the idea of this. But of course, if you are asking me about the Lagrangian, well, I know what is the Lagrangian of the standard model, but if I start to it will be like playing here, and there's nothing concrete yet. But that's more or less the idea which I am thinking about, and it still is in the early stage. So then, well, about the mechanism, no, I have not shown any mechanism right now. And then now I jump to gravity. Any other question so far here?
So this isn't a Nambu-Goldstone, right? Because it's
No, in this case it's different because this is a parenthesis in the talk. No, the Nambu-Goldstone boson. I already finished that part. Here I wanted to mention that actually these triangular relations and these arguments of symmetry, or the fact that the other parameter superposition gives you zero, can be used also for analyzing this kind of problem. Well, the battery is finishing, so I have to connect it. Yeah. And I will close this talk with the power of gravity. In gravity, I will show that the in gravity, I will show that the Hawking radiation, and Hawking is right because we don't know if he's right in his calculation. I mean, don't misunderstand me. Hawking is brilliant. He's a genius. But I mean, it doesn't mean that all what he did is right, no? Then some people claim that his thermal spectrum is not really thermal, that there are non-thermal modes, etc. But I will omit those aspects, and I will focus only on the thermal spectrum he found. Then in that case, I will mention, well, not exactly Nambu-Goldstone bosons in gravity because I will not portray them, but let's talk about black holes. What is a black hole? It's a compact object, very compact, such that you can store the mass inside the gravitational radius. Let's put an example. If I take the air, the mass of the air, and I put in a volume inferior to a radius of 3 millimeters, that's a black hole. That's a black hole. Small, but it's a black hole. Naturally, they form with the collapse of a star. So whenever the mass is inside 2GN, well, for the spherical symmetry, you have black hole. If the mass is outside 2GN, that's not a black hole. Okay? The gravitation is so strong that nothing can escape, not even the light. The light cannot escape. How can we see them? Because of the gravitational influence they have around. And because, of course, the light coming around behind them surround them completely. We can see them. We can see the event horizon size. Hawking, however, predicted that if we use arguments of quantum mechanics, the black holes can evaporate. they can emit particles. That's called Hawking radiation. He explained it in different ways. One simple way to calculate gravity is using the definition of surface gravity, which is what every student of bachelor or master do initially when they don't deal with quantum field theory. And of course, take into account that the black holes, they also have thermodynamics. Because of course we have the entropy of Bekenstein, who passed away already. Hawking, who passed away, he did the temperature, etc. The entropy measures the amount of information the black hole hides inside it. And the information paradox, which was formulated by Hawking, says that since the thermal spectrum emitted by the black hole doesn't have any information, then what happened with information? We have to wait until the black hole evaporates completely, or what is the reason? Then there are many proposals, some of them coming from dualities, etc. Some people say, no, is that he didn't include the non-thermal modes, or not everything is thermal, whatever. But here I will take the spectrum to be thermal, and I will analyze, I will use similar arguments which I showed before about the Nambu-Goldstone theorem. This part I will not touch it. I wrote something before that, the equivalence between evaporation and quantum depression in condensed matter when there's almost zero temperature, the particles. This, I will not touch this part. But what I will mention is that what Hawking did was to compare two vacuums. He compared two vacuums, one vacuum before the formation of the black hole, and the other vacuum after the formation of the black hole. This is all. And you can define two vacuums easily. I will do it here. As usual, we define the vacuum. You can define, for example, you have A and B. You can define a vacuum like this, and a different, let's say before the formation of the black hole, a different vacuum, 0 bar, after the formation of the black hole. But when you compare the two vacuums is where you have discrepancy, and this is where the spectrum of radiation emerges. Then a long time ago, I was wondering why this looks like somehow as this kind of mechanism of spontaneous symmetry weakening. If we take the order parameter as the particle number operator, because before the formation of the black hole, you have 0, and after the formation, you have 0, whatever it is. It's thermal, whatever. But then let's find a Lagrangian reproducing the black hole evaporation process. But before that, let me explain, of course, the comparison of vacuums can be also seen from the Bernoulli diagram, future null infinity with the past null infinity, etc. This is the definition of surface gravity. You will see some mix of parameters. It's because I mix up with the quantum depression issue, which I did before also. This is the quantum field. The quantum field before the formation of the black hole in terms of single modes. And this is the same quantum field after the formation of the black hole. Modes will go to the infinity, and those modes that cannot escape. Okay? And these modes are the ones you compare. B and A, you compare via Bogolubov transformation. These are the Bogolubov. Whenever this coefficient is different from 0, there is discrepancy between the vacuum defined by A and B, and then you have particle creation. How do you see that? Because if I define the vacuum for A, and I apply B, or better the other way around, I apply the vacuum for this, and I define A over this same vacuum, then of course there is one coefficient which creates, it will give me minus B star 1. It will create particles. So it means there's discrepancy in the way how the observer before the formation of the black hole defines the vacuum, and the observer after the formation of the black hole defines the vacuum. Then why not to construct a Lagrangian to see what happens? I constructed a Lagrangian. These are the kinetic terms, but the kinetic terms you neglect them when you analyze the equilibrium conditions. And this is the potential for the particle number operator which reproduces Hawking radiation. It has a quadratic term, cubic term, and quartic. Here the novelty with respect to the standard processes of spontaneous symmetry weakening is this term, the cubic. This cubic term normally doesn't appear. Then, of course, when you calculate the BDN equals 0, you obtain two solutions, n equals 0 before the formation of the black hole, and n equals 0 after the formation of the black hole. Yeah, you have a question.
Okay, so set up the rate in the symmetry plane.
Yeah.
Then what symmetry does it bring?
That's a good question. Because when you have a black hole, the black hole can be defined with mass, charge, angular momentum. Then you can change, you have the entropy, no? The entropy measures the amount of information the black hole has inside. So you can make any change inside, whatever is inside, as long as you keep the mass, charge, angular momentum, that's the symmetry which I am considering. So symmetry on the exchange of configurations internally such that you keep constant the mass, the charge, and the angular momentum. The key points of the no-hair theory, no? Then that's the symmetry I have in mind. But then let's go back to the issue is that you can demonstrate that only when m squared is different from is smaller than 0 is where you have an n different from 0, and if you calculate the Euler-Lagrange equations and solve them, you obtain the spectrum of Hawking. This is well, I wrote this in here, and then one way to visualize this is, of course, before the formation of the black hole, trivially, after the formation of the black hole, non-trivially. But if it's true that the particle number operator is another parameter, it means that in one instant of time, if you sum all the possibilities, there must be a bunch of possibilities for this number. It should vanish. But if this is true, it means that some particle number operator should be negative. So the picture, there are two ways to analyze this. When Hawking formulated his black hole evaporation, he imagined pairs of particles create outside the event horizon. And he said, one of them go inside and the other escape. So I think the positive numbers are, of course, the particles which escape. The negative numbers are particles which you enter the black hole. Or you can interpret those negative numbers probably with antiparticles coming out from the black hole. Anyway, this doesn't solve the information paradox yet, but still, of course, it's a good way to interpret, I think, the black hole evaporation process. I think this is a little bit of the same. Of course, what is Nambu-Goldstone boson here? Well, it's not a cinematographic movie. It's not a movie of the boson moving into the event horizon or so. The Nambu-Goldstone boson here is just a representation of all the possible growing states consistent from mass, charge, and angular momentum. Because anyway, what a Nambu-Goldstone boson do is to swing over all the possible growing states at the end. So that's another way to see. With this one, I want to close it. The conclusion is the Nambu-Goldstone theory is a natural consequence of the constraints coming from Quantum Yang Baxter equations, whatever it is. Of course, by extending the other parameter to a tensor, we can find the relations. I think I forgot to write something, but the idea is Hawking radiation is a consequence of a spontaneous symmetry weakening of some internal symmetry, which is related to the change of configurations, keeping the mass, charge, and angular momentum fixed. This is a different issue because I didn't talk about quantum depression. But you should know that there is an analogy between condensed matter systems and black hole evaporation, and that's called quantum depletion. Is when the condensed matter system or some fluids reach almost the zero temperature. They are not supposed to evaporate, but still quantum mechanically they emit particles. That's analog to the Hawking radiation. And the way how they calculate is exactly what Hawking did for finding the spectrum of radiation for black holes. Well, this is not completely sure, but I just say that some relations, not necessarily actually, I put quantum Yang Baxter, but actually the Yang Baxters just appear at the end, but let's mention that some relations, or there are ways to interpret the neutrino oscillation, which help us to constrain the values of the mixing angles and the eigenvalues of mass. Take into account that the experiments on neutrinos, they don't measure the eigenvalues of mass. They measure differences, delta M1, 2 square, delta N3, 1 square. And this is how they conclude M1 is close to N2 and these kind of things, but they cannot calculate M1, N2, or M3. Still, with this triangular formulation, I could calculate N1, N2, and N3, but this formulation doesn't tell me yet what is the mechanism of generating mass for the neutrinos, which is something that nobody knows right now. But of course, there are many theories and many hypotheses, many things. And the response will come with quantum with field theory, as Professor Hikaru Kawai has said. You have to construct a Lagrangian, which explore those interactions. And that part, of course, is in process, but it's still not conclusive. Then this is my presentation today. Thank you very much. Of course, you already asked questions, but you have more questions. Yeah.
Generally, like Yang Baxter equation means that the system is integrable.
Yeah, people use in that way, yeah.
So
Sometimes.
Here, basically, you say that all system with spontaneous symmetry breaking will be integrable. I think it's really unlikely.
Well, I don't think in sense of integrability or not. What I'm thinking is in how the person Nambu-Goldstone bosons interact. And I think Yang Baxter has many ways to be applied. No? One way is what you say, but another way is that you have a bunch of particles, and you can reduce that set to an interaction of pair of particles. For example, that's one way to use Yang Baxter also. And the way how Witten probably Costello didn't talk in that conference, but the way how Witten showed in that conference was just analyzing interaction between pairs of particles. This is the way how I use the Yang Baxter here. I analyzing the interaction of one Nambu-Goldstone boson with another, and when they move around the degenerate vacuum.
Basically, if there's a function like Nambu-Goldstone movement, the interaction may reduce to like the interaction pairs Nambu-Goldstone.
I cannot say that definitively, but it looks like that if you use this approach. Yeah. Well, of course, take into account that well, normally nothing happens, but this is interesting is when the 2 degrees of freedoms become a single one, because in that case you can solve the counting problem. For example, you can explain why 2 broken symmetries correspond to a Nambu-Goldstone boson. It doesn't mean that the theorem is failing. It doesn't fail. What happens is those 2 degrees of freedoms are fusing in a single one. And of course, you cannot expect the dispersion relation to be the same. The dispersion relation of something which merge with something else will deform. No? And that deformation comes out to be quadratic. That's more or less the picture which I'm showing here.
I'm curious, like what kind of interpretation would this have with Unruh, the Unruh effect? So, like, if I have an observer which accelerates and sees number of particles different from 0, can I not apply the same sort of reasoning and say, oh, maybe there's some spontaneous symmetry in that?
Well, yeah, the Unruh phase. I think for those who don't know, I think all of you know probably. Unruh find an alternative way to derive the spectrum of radiation when an observer accelerates. In vacuum, in flat space-time, he can perceive a spectrum of radiation, and artificially, because it's accelerating, he creates an even horizon. Actually, there is a surface. Yeah, in that case, would be like if there is no acceleration, the vacuum is trivial. The other parameter is the particle number operator. When the observer accelerates, it's breaking some symmetry spontaneously.
But I'm not breaking symmetry. Flat space.
Not the obvious symmetries, but there might be some symmetry or equivalent symmetry. Because in the case of black holes, the symmetry involved, that symmetry is the it corresponds to the internal configurations, not connected to the information of the black hole inside. And now something which I forgot to say is that the black hole never reaches an equilibrium condition, because when it's in vacuum, of course, it has to select one of those possible vacuums, and when it does it emits particles, and then the process repeat and repeat and repeat again. So the black hole is always trying to find a stable equilibrium condition, but never reaches it. This is more or less the picture I am trying to portray. In the case of Unruh, I had to think a little bit, but more or less the response should be that. But another thing is that, what is the surface gravity? The surface gravity is the acceleration perceived by an observer. The observer has to be static somewhere in the infinity, and he see how these guys move toward the black hole or something, how they accelerate due to gravity, and that's what we calculate in this. That's the simplest way to calculate the black hole temperature, no? It's a simplified way with this invariant of acceleration, but in the sense of Unruh, of course, there must be some symmetry, which is broken, and the other parameter is the particle number, but of course, it's not the space-time symmetry. It's not the space-time symmetry.
It's difficult for me to. I feel like it's analogous to spontaneously broken symmetries, but it's not exactly the same, right? It's something different. Because I don't see in the case of Unruh, there is no SSB happening.
Could be. I will think about the Unruh case. That's a good question. And that's why these seminars are nice, because people say things, and then after I go home and I start to think about it. Well, let's say that the case of Unruh, yeah, I will consider it, but for sure it's not the space-time symmetry was broken. In the case of the standard case, the particle number, but it's obvious that the particle number operators should be the order parameter. And I must remark that if we try, because of course one complaint, or let's not call complaint, something which somebody can argue, because the reference argued this first, is how do you guarantee that this Lagrangian is connected to gravity? Well, first thing is that the Unruh probably also. The Hawking radiation most likely is a generic issue, a generic process, in the same way as we have universality in material science, that we have many like the same Lagrangian explaining the same materials and the same process. But beyond that, what I want to say is that if we use the standard Einstein-Hilbert action, of course, you will not obtain Hawking radiation because it's classical. There's always something else, no? People normally introduce a scalar fair, whatever. But there are some clues that there are some additional terms you have to include to the Einstein-Hilbert action in order to reproduce naturality Hawking radiation. But at the end, they have to be consistent with this Lagrangian, which I showed here, which is the Lagrangian with quadratic, cubic, and quartic, maybe some resummation, some resume Lagrangian, finishing vain like that. And that could be an intermediate step between classical GR and what we call quantum gravity, because remember that the Hawking radiation effect is a semi-classical effect. It's not quantum perfectly, it's not classical perfectly. Hawking took a classical background and put a quantum field moving around. But right now we don't have a quantum theory of gravity, so but for sure there should be some Lagrangian in between. No? Some Lagrangian, some expansion, some whatever. Could be. Then, well, thank you. That comment is quite good, actually. I think I will think about the new case. Question? Who is the host? You are the host, yeah.
Oh,
Yeah, you're the one. I was waiting for the host. Well.
If there are no more questions, thank you very much.
Okay, thank you. Okay. I was waiting. It's the usual, I'll say, perhaps I'm why. That's what I will think about your comments. This issue of dimension. It's a question I always receive about this. Nobody got the match that.
对，你也会去，或者最后来那个那个，我就有时候就。
OK，今天。